Okay, hi everyone. Hopefully you can hear me this time. I'm going to wait a couple minutes to see whoever wants to join live can go ahead and join, and then I'll put myself on mute and come back in a couple minutes to go ahead and start answering the questions. Okay, for those of you that are just joining, I'm just going to wait a couple more minutes to see if anybody else joins, and then I'll come to the questions on Piazza. Okay, I'm going to go ahead and get started. So our first question is, for the spanning tree protocol, the stabilized spanning tree is much more like a breadth first search tree with lowest ID at the root. What's the reason not to run the algorithm at the global level instead of a distributed one? And the answer of this one is because to run the algorithm at a global level, you kind of need to know like the entire topology at the beginning so that you can run the algorithm. But in our case, and in the real world case with different switches, like each switch is only going to know its direct neighbors that it's connected to and its own switch ID and their switch IDs. It's not going to have a picture of the entire network topology. So we have to run the algorithm at each individual switch and kind of base it on the passing of messages or packets between the switches so that each switch can learn about the entire topology from its neighbors. So like each switch knows its own neighbors, and then it passes that information to all of its other neighbors so the information can kind of propagate throughout the entire topology, but one switch doesn't know everything to begin with. So that's kind of how we have to do it for our algorithm, why you have to base the entire thing on sending messages, and you can't look into the data structures of your neighbors at the beginning. Okay, and the second part of that question is, how are the unannounced topologies going to look like? For example, are they going to stress our designs like feeding a topology with 1 million nodes? The answer to that one is they will be a little bit more complex than some of the sample topologies we gave. Like the sample.py, definitely that one's pretty simple. There'll be typically corner cases, so it might be something that's not completely straightforward. Like the tail topology in the provided ones, that one's a little bit of a corner case. It's a little more complicated than just like the basic loop node because it originally converges on one root, and then at the end of the tail it finds the actual root, so it has to go back and propagate that through the nodes that have already converged. So it might be things like that where it's kind of a corner case, something a little bit different than a simple topology. We probably won't be feeding something 1 million nodes, but it might be more nodes than you see like the 5 or 6 or 13 in some of the complex topologies that we provided. It might be more than that. It won't necessarily be having the root at 1, so you might have a larger switch IDs, and then let's see. There might also be like non-consecutive numbering, so make sure your algorithm isn't based on that. But in general, it'll just be a little bit more complex, maybe some like loops or extra nodes than the provided topologies. So I encourage you guys to kind of come together and post different topologies that you guys can think of on Piazza and kind of use that as a testing tool. See what kind of complex topologies that you guys can come up with. Okay, moving on to the next question. For P2, could you comment on how to approach send messages in topology.py and building the objects to use that function? And it looks like he kind of later understood that a little better, but I'll go ahead and answer in case anybody has a similar question. So to get an idea of like how to create the message objects, take a look at the message py file that's provided, and you'll see the different attributes of the message class that we're expecting you to create in your message object. And then you need to create or instantiate an instance of the message object within your switch.py class, and then call the send messages function with that object as a parameter. And one other thing I'll just point out, again, it's in the project, I think it's in the description, it's definitely in the comments. When you're using the send messages function, make sure you're calling it as the self.sendMessages. Don't use the self.topolink.sendMessages, because you shouldn't be using the topolink parameter at all in your code, because when we grade your code, we're going to use a differently named version of this parameter. So if you are using it, then it will not pass the grader. And again, the reasoning for this one is that if you can access the topolink variable, you can get some information about like the internal structures of the neighboring switches, which is kind of against the spirit of the distributed algorithm. And then the second part of this question is, this is more clear now, but hope there can be some discussion by you on the data structure defined in the first to-do. I'm trying to create a data structure in the constructor, but that only has a few members below. Please comment on the data structure as it relates to that constructor and process message. That would be helpful. I have watched the video multiple times. And then it has a comment from the superclass constructor that has the self.switchID and the self.links. Okay, so at the beginning, your switch will know its self.switchID, which is its switch ID, and then the links, which are its directly connected neighbors. For your data structure, you also want to define this in the constructor, but it won't necessarily, you're not going to be filling it up in the constructor. This is something that you'll be updating like each time you call process messages. So I'm not going to give like too much structure on how to create the data structure. That's kind of up to you. There's a lot of different ways that can work, but typically things that you're going to need to track are, you need to keep track of who your switch thinks is the claimed root. So it's not going to necessarily be that switch. It'll be whoever has the lowest switch ID. So whenever you get a message with a lower switch ID, you'll need to come back and update that one. And then you also need to keep track of the distance to root, which you'll also need to update like each time you're processing a message. And then the big thing that you need to keep track of is the active neighbors that that switch has in its spanning tree. So as far as data structures that you can use, you can keep these as like different separate parameters. Some people do that, like you have like an integer type variable for the distance to root, that works, or like a list for the links or the active links, and then you keep updating that list every time you process a message. Or some people have used a dictionary. So the format is really up to you. It's whatever you find easiest to work with, but list and dictionaries are some pretty good starting points for keeping track of the links. But yeah, as far as like having the self.switchID and the self.links, those are things that you need to know in the beginning, and you'll use those to send out your initial messages, but they don't necessarily play into creating your other data structure. That you need to like set up in the beginning, but you'll fill it over time as you run the process message function. Okay, next question. is back to project 1. So for project 1, I would like to understand how we can dynamically label our variables. I have in a loop that xx equals self.add switch s1. The next loop will have s2, s3, etc. But are we also required to have xx be dynamically variable? This is where I'm stuck. Okay, so the answer to this one is no. You don't have to dynamically name your variables. When we say we have like the naming format, that's just for the parameter into the self.addSwitch method. So like your add switch and then the S1 there, that's what you need to dynamically change. So you have like self.addSwitch S1, S2, S3, and then something similar for the host. But the variable names themselves don't matter at all. You can name those whatever you want. You can name them all switch and add them to a dictionary or a list to keep track of them later. That's fine. So the only thing that you need to change is like the name parameter that goes into the add switch or the add host methods. And you can use like different kinds of Python string manipulations to dynamically label those, but don't worry about the variable names. Those don't matter at all. Okay, so next question. For project 2, I've gone through the videos, readings on STP, and I believe I have a solid grasp on how STP works. I'm not sure how to start the actual implementation though with the Python code. I've been trying to start with creating the data structure, but have made no progress. Any recommendations would be greatly appreciated. Okay, so I talked a little bit about the data structure above, so hopefully that will help a little bit. As far as getting started on the algorithm, what I would recommend, and I've seen a couple students say they've done something similar in the Slack channel, is kind of start with the very simple topology, like start with sample.py and even write out the different messages that you can think of how it worked by hand before you even start implementing, and then like start writing your code based on that. So start with like the sample and then get it to send the very basic messages like and solve that one. And then like if it's a short example, when you write them out by hand, that one's kind of easy to compare, and then get that one working. And then once that one's working, you can kind of expand a little bit and then work on like one of the simple topologies with only a couple nodes, and then kind of build up until you can get the whole thing working. So hopefully that will help. Just kind of make it an iterative approach and start with some really simple examples, and then you can start working on like where you might have gaps in your algorithm to handle some of the complex things. Like I think the complex loop topology and the tail topology are probably the hardest ones for your algorithm. Okay, and the second part of this is, would you be able to cover how to access the different parts of the message in Switch PY as variables or point to a reference? I figured out how to create the message object, but only with adding in my own values. Okay, so this one, in your process message function, you have the message coming in as a parameter, and you can access that. Okay, so if you look back at the message class, there's 5 different parameters: the self.root, distance, origin, destination, and path through. These are the same parameters that you can access in the switch class. So to get those, you just have like your message as its pass in the parameter, and then just a dot, and then whatever parameter you want. So instead of like self.root, like you see it in the init of message.py, you would just have message.root or message.distance, and you can print those out to access those. So that's similar to accessing any object in Python. Okay, and then a follow-up as a question to how you describe data structures. I was under the impression everything you need to keep track of would all be in one list dictionary, but based on what you said, it sounds like that is the wrong approach, and I can separate what I'm keeping track of. Yeah, like it's really up to you. If you find that keeping everything in a dictionary works, that's definitely fine. I think as far as a list, it would be hard to keep track of everything. Like you could have maybe one list for your active links, but it would be hard to keep track of the root and your path, your distance to root within the list, same as the active nodes. But if you have everything in a dictionary with a specific key, then you can definitely keep everything together, and you might have like a dictionary with one object as the list for the active links. That's one approach. So it's really, there's not one right approach to do this. It's whatever you find easier to go back and access these and kind of update along the way. So if you find that keeping everything together is difficult, then try splitting it out and see if that makes things easier for you. Okay, the next question is, can you please discuss pass-through and how it relates to the overall algorithm in the videos? An example with pass-through, I think it's actually called the path-through if you're watching this later, and data structure laid out in a similar fashion to the videos would be great. Okay, so there's a couple of good discussions on Piazza already. If you want to check out at 159 or 129, those have some good class discussions on that variable. But as a general description, the path-through is used when you have an upstream neighbor that isn't using a downstream neighbor to reach root, but it needs to keep that link open so that its downstream neighbor can reach root. So an example for this one would be in the sample.py, we have the 1, 2, and 3 connected, and 2 only needs to keep the link to 1 active for it to reach root because 1's root and it's only 1 hop away. So 2 has no need to keep the link to 3 activated. But 3 needs 2 to keep that link activated because it needs to go through that link to reach 1, which is the root. So you might want to have something set up like for 3 to send a message with the path through set to true to 2 and say, hey, I'm using your links to access root, so please keep it activated. So that's an example of when you would use the path through variable. But it's definitely not required. I think once you maybe understand how to use it and what it's for, you'll find it simplifies things a little bit. But in the past, we didn't use this variable, and it was added kind of to keep things simple. So it's not strictly required, but it can definitely simplify things. Okay, any counsel on the structure of logic within process message to process the messages and update the data structure would be great. Having issues where it will not stop. Okay, so I'm not going to go into too much detail about the logic because that's kind of what we're expecting you guys to figure out. In general, for the algorithm, like you're going to want to update your data structure if there's a new root or if you find a better path to root. Those are when you'll want to update your data structure. And at the same time, every time you update your data structure, you should be sending out a message to your neighbors. But if you're having an issue where it won't stop, you probably should go back and check your logic where you're sending out those those messages to your neighbors. If it's not stopping, make sure, a couple things to check, make sure that you're sending messages only when you get an update to the data structure. Like if you're not updating your data structure at all, don't send any extra messages. There's nothing extra that you need to tell your neighbors, so you might get into some kind of infinite loop there if you're always sending a message update regardless of whether you're actually making an update. And another thing that might get you into a loop situation where it's not stopping is if you're sending messages back to the switch that sent you the message that triggered the update. So that can kind of get into a loop there. Let's see. Okay, so I think that's kind of all for that one. Let's see. Okay, so the next question for P1, what is the best way to verify the actual host switch linkage layout? Is there a command that generates an actual PNG image file of the network layout similar to those shown in P1 PDF? No, there's not a command that I know of that will do a printout. The best way is to use, I think, the links command and the net command and dump, I think, is the other one. Those are the three that kind of, the links command is probably, if you're looking specifically for links, that one is one of the best commands to get an output of all of the links that you've created and what they're connected to. So from that, you can kind of draw the image, but there's nothing that's going to draw it for you, as far as I know. Okay, there's no more questions that I see. Let me refresh and I'll stay online if there's any more added or any follow-ups, anything I've answered, anything's not clear. Post a follow-up and let me know. Okay, yeah. I don't see any more questions, so I'll hang out here for about 10 more minutes if there's no additional questions. If you have any additional questions, please go ahead and post the Piazza thread so I can follow up there. Okay, so the next question is, after the two methods in switch PY either send, receive a message, is that where the data structure will then be updated if necessary? Okay, so when a switch receives a message, it needs to do the different logic, like comparing the root ID with its current claim root and comparing, if it's the same root, comparing the shorter path. If any of those will trigger an update on that switch based on the message that was received, then it needs to update its data structure and also send an update message. So the receiving the message is really what will trigger the update to the data structure, and then that will also trigger the sending of new messages to the neighbors. Okay, and then a follow-up to that. So in the process messages method, you could end up sending more messages from that. Yes, that is kind of the essence of the algorithm. You'll send your initial messages from each switch in the send initial message function, and then that will kind of trigger everything to start. And then every time in the process messages function, you need to send new messages every time there's an update. So yes, that's kind of the basis of the algorithm, is continuing to send updates as long as you're processing messages and a change is made. And then eventually your algorithm will stop when everybody has converged on a root node, everybody has their shortest path to root updated, and there's no more messages to be sent within the process messages. And that's when it will end and print out the final output. Okay, so next question is the data structure for holding a switch's current view of root, distance to root, etc. supposed to be made when the initial messages are sent out? So you should make your data structure in the constructor within the init function, and then the send initial messages will be separate, but it'll be based on your links so that you know like who your direct neighbors are and who you can send the messages to. And then within the process message function, that's when you'll update your data structure. But go ahead and create it within the constructor. Okay, and then one more. When I create a list in the init and try to access that list in process message, I get a global name is not defined error. Okay, so when you define a list or anything else, make sure that you're using the self dot and then your list so that it's a class variable for that one, and then see if that helps you get rid of the global error. And then when you access it, also use the self dot structure. And like for an example of that one, if you're not familiar with how to use the self, look at the message class and see how like the self.root is set in the init function, and then later on, or like the self.paththrough, that same variable is used like in the verify message function. Okay, so looking at self.root equals claimed root, the claimed root excuse me, portion is just to use for the parameters. However, you cannot use claimed root through the rest of the code. You have to use self.root everywhere else in message.py. Let me go back. Okay, yeah, so in message.py, within the init function, the things that are called like claimed root, distance to root, origin ID, destination ID, and path through, those are basically your parameter names, and that's like what you'll be passing in when you instantiate the message object within the switch.py class. But the actual variables that it's setting to be accessed throughout the rest of the class are the like self.root and self.distance, and it sets those equal to your parameters. And then the ones that are named as the self.attribute name, those are the ones that you'll be able to access throughout the rest of the message class. So when you set it up as your switch class, it'll be something similar. Okay, the syllabus references computer networking, a top-down approach, 6th edition. However, I was wondering if one could use the 7th edition of the book for this course. Specifically, when studying for the exams, can we use the same chapters as specified for the 6th edition? This textbook is kind of optional in this class, so it's really just for your own reference. Like, we're not going to pull any test questions word for word out of the textbook. Since it's optional, I think the 7th edition should definitely be fine. As far as the same chapters, I'm not 100% sure if the chapter numbers line up. I think as long as I think Maria posted some like recommended reading with the chapter numbers, as long as the chapter names line up, then I think you can definitely use the same chapters. Otherwise, you might just want to check and make sure if the numbers are different, it should have a similar title that you can read and it'll have the same information. Okay, there's one question about P1, which I just went back to double check. In P1, the dynamic topology part has user specify the bandwidth and delay. However, there is no reference to loss. Can we enter an arbitrary loss rate for the dynamic topology file in P1? The best thing to do for this one is just leave it out. Loss isn't a required parameter. So just worry about specifying the bandwidth and delay. If you want to experiment with the loss rate, then that's fine. But I think for the final version that you turn in, just leave it out to make sure that there's no issue with the grading. Okay, I'll hang out for about 5 more minutes. If anybody has any additional questions, please go ahead and post them to Piazza. Otherwise, I'll let everybody get back to their Saturday. Okay, well, I don't see any extra questions on Piazza, so I'm going to go ahead and hang out for this week. For those of you that joined live, thanks for watching, and I'll see everybody again this Thursday.